All right, let's talk about something we all take for granted, turning the wavy AC power from a wall outlet into the smooth, stable DC power that all our electronics crave. It seems simple, but it's actually not. Today, we're going to get our hands dirty and dive into the real-world engineering challenges of designing rectifier circuits that can actually work in the real world. So, the dream is always to get this perfect, clean DC output. But just look at these current waveforms that the rectifier diodes are dealing with. Those aren't nice, smooth sine waves, are they? No way. They're blocky, they're abrupt, and this jagged reality right here is the source of all our problems. And today, we're going to figure out exactly how to tame it. So here's our game plan. First, we're going to start with a perfect, idealized circuit, just to get a handle on the basic physics. Then we'll peel back the layers and uncover all the hidden problems that ideal model creates. I'm talking about things like harmonics. After that, we'll design the fix using filters. And finally, the best part, we'll prove our design actually works using simulation. It's a full engineering story, from problem to proof. Okay, let's jump into step 1, understanding the ideal case. To really get to the bottom of this, we'll start with a simplified model, a three-phase rectifier that's powering a highly inductive load. Think of something like a big industrial motor. You see, when you have a big inductor on the output, it acts like a flywheel for current. It just wants to keep things smooth. It resists any changes, and that means the current going to the load becomes almost perfectly continuous. It's like a flat DC line with practically zero ripple. This is our perfect theoretical starting point. So we did it. We got a perfect DC current on the output. Awesome, right? Well, there's a catch. There's always a catch. To create that beautiful, smooth DC current, the rectifier has to draw current from the AC grid in this ugly, blocky, square wave shape, and that distorted current gets pushed right back into the power grid, which is something the utility company, and frankly all the other equipment connected to the grid, really doesn't like. And this, right here, this square wave input current, this is the absolute root of our problem. It's a giant red flag telling us we're creating some nasty, unintended side effects. And this is where the real engineering challenge begins. We have to clean up our own mess. So how in the world do we analyze a messy wave like this? Well, this is where the genius of a guy named Joseph Fourier comes in. He showed us that any repeating wave, no matter how weird it looks, is really just a bunch of simple sine waves all added together. Our square wave, it's made of the main frequency we actually want, plus a whole cocktail of unwanted, higher frequency waves. And we have a name for those. We call them harmonics. And we can actually put a number on how messy this is. The harmonic factor for this current is over 31%. Think about that. That means nearly a third of the current we're pulling from the wall isn't doing any useful work at the frequency we care about. It's just creating electrical noise, pollution that can mess with other electronics, and even cause transformers to overheat. And all that distortion, it has a direct impact on our efficiency. The power factor, which is basically a grade on how well we're using the power from the grid, drops from a perfect score of 1 all the way down to about 0.955. We're essentially drawing more current than we need to, and you can bet the utility companies are not fans of that. Okay, so let's recap. We've got two big problems, right? On the input side, we have all this harmonic distortion polluting the grid. And on the output side, we still have some voltage ripple, making our DC supply a little unstable. Luckily, the engineering solution for both of these problems is actually pretty elegant. It's powerful. The solution is filters. And here's our toolbox. These are the gadgets we use to fix everything. As you can see, we can use DC filters on the output, things like the L, C, and LC filters you see on the left to smooth out that DC voltage. And on the input side, we can use AC filters, like the one on the right, to clean up the current we're drawing from the grid. For now, let's zero in on the output side of things. We're going to walk through the design of a really simple but incredibly effective DC filter, the capacitor filter. We're going to see exactly how we can squash that annoying voltage ripple. This waveform right here shows the magic of the capacitor filter in action. See that rising part of the wave? That's the capacitor charging up, storing energy right as the voltage hits its peak. Then, as the rectified voltage starts to dip down, the capacitor takes over. It acts like a little temporary battery, slowly feeding power to the load. It beautifully fills in those valleys, turning a really bumpy ride into a much smoother one. Now, before we start designing, we gotta speak the language. This table lays out the key terms we use to measure ripple. And the most important one for us, the number we're really chasing, is the ripple factor, or RF. It's basically the size of the ripple compared to the average DC voltage. This is our main design target. And the design process itself is just beautifully logical. Step one, we define our target. How much ripple can we live with? Let's say we're aiming for less than 5%. Step two, we use the physics-based formulas right out of our textbook to calculate the exact capacitor value we need to hit that target. It's a clean three-step process. So let's actually apply this. Following the example from our source material, the math tells us that to get our ripple down below that 5% goal, we need a 175 microfarad capacitor. And this is a perfect example of what engineering is all about. We take an abstract goal, less ripple, and we translate it into a concrete physical component that we can actually go out and buy. Okay, so we've done all the math. Our calculations point to a very specific component. But as good engineers, we always have to ask, does it actually work? Well, before we go and build any real hardware, we can use amazing circuit simulation software like PSpice to verify our design. And this is what that looks like. Here in a simulation tool called PSpice, we can build a perfect virtual replica of our circuit. We can plug in the exact component values that we calculated. This lets us test our entire design and catch any potential problems before we spend a single dime on physical parts. It's incredibly powerful. And the results are in. The simulation shows we get a nice, clean DC output of about 114 volts. And the most important number, the total harmonic distortion, comes in at just 5.6%. This is fantastic. It's super close to our target, and it proves that our calculations were spot on. Our filter design works. And this brings us to one last really crucial question that every single practicing engineer has to ask. Okay, our design works, it's functionally correct, but is it the best design? Sure, a bigger capacitor might give us even less ripple, but it's also going to be bigger, heavier, and more expensive. So how do we balance performance against these real-world constraints of cost, efficiency, and physical size? Well, that process of optimization, that's the real art of engineering. And that's a topic for our next discussion.